Okay, so get this. Imagine a structure, like created by a black hole, but it stretches across a vast portion of the universe.
Wild, right. Well, that's what we're diving into today. Giant radio galaxies.
What's fascinating is we're talking about these incredibly powerful jets. Jets of energy and matter blasted out by supermassive black holes at the centers of galaxies.
And get this. Scientists have just discovered a new record breaker.
Oh, wow.
They've nicknamed it Porphyrion using the LOFAR telescope. And it's not just its size, though it is mind-bogglingly huge, but what it tells us about the early universe, like how these cosmic jets even work.
Yeah, Porphyrion is a cosmic titan, no doubt about it. It
Yeah.
spans, get this, 7 megaparsecs.
7?
But before we get lost in just how huge that is, let's take a step back for a second. How do we even measure these objects across such vast distances?
You're talking about redshift-space, right?
Yes,
It's
yeah.
like, how do I explain this? Imagine trying to hit a moving target, but you're on a platform that's moving too.
I see what you mean.
The universe itself is expanding and everything it's in motion, so. It distorts our observations, for sure. Makes it incredibly tough to pinpoint an object's true size and position. Actually, one of the research papers we're looking at today by Korea and their team, they tackled this problem head-on.
I was just going to ask you about that.
They focused on how redshift space affects how we study cosmic voids, basically vast, underdense regions in the cosmic web,
Like the empty spaces between those galaxy filaments.
Exactly. They developed this really clever mapping technique, basically connecting what we see in redshift space back to the real universe.
So correcting for the distortion.
Precisely.
Yeah.
They found that large voids that we identify in, observational data, they almost always have a real space counterpart.
So they're not just an illusion caused by redshift.
Exactly. They're really out there. But let's get back to these giant radio galaxies.
Okay, yes. 7 megaparsecs. Can you put that into perspective? I mean, how big is that really?
Okay, so Porphyrion is about 66% of a typical cosmic void's radius at that redshift, of course. Now imagine shrinking Porphyrion down to the size of a human hair.
Okay, I'm imagining that.
A typical galaxy would be about the size of a grain of sand. That's the scale we're dealing with here.
That's mind-blowing.
And it used to be thought that these giant radio galaxies, they were incredibly rare, but there's a new study out by OE and their team, and they completely challenged that assumption.
Yeah, they've compiled this incredible catalog. Over 11,000 giant radio galaxies.
It completely changes our understanding of how common they are.
It does. So how did we miss so many for so long?
The answer lies in how these objects were identified. They used a really interesting combination of, advanced techniques, you could say, machine learning for one, to sift through these massive data sets from telescopes like LOFAR.
Right, and LOFAR scans huge portions of the sky, right?
Exactly, and they also use citizen scientists.
Wait, really? Everyday people were involved in this discovery.
They harnessed the power of something called the Radio Galaxy Zoo project. Volunteers, everyday people, helped classify these objects just based on their radio images.
That's amazing.
It just goes to show you how collaborative science can lead to these groundbreaking discoveries.
Absolutely. So, back to Porphyrion, our cosmic record breaker. How did they manage to capture such a detailed picture of this thing?
It was real teamwork. It wasn't just one telescope. They combined data from LOFAR, the upgraded giant metrowave radio telescope, and even optical observations from the Keck-Eye telescope.
So each telescope provided a different piece of the puzzle.
Precisely. And what they found really challenged what we thought we knew about how these giant radio jets work.
Because it was active when the universe was much denser.
You got it. Scientists thought that in the early universe, these jets would be disrupted by the surrounding environment. But Porphyrion's jets, they remain stable across these incredibly vast distances.
So what does this tell us about jet physics?
It tells us we still have a lot to learn. There are aspects of jet formation, propagation, and stability that we just haven't fully grasped yet. Porphyrion is making us rethink our models.
And these giant radio galaxies, they're not just pretty lights, are they?
No, they're not. They play this crucial role in shaping the cosmic web.
They're like cosmic architects.
A perfect way to put it. They're powerful forces, heating up and pushing matter around. They influence where new galaxies form and even how the cosmic web evolves over, billions of years. OE's team calculated that Porphyrion, just this one giant radio galaxy, released as much energy as entire galaxy cluster mergers.
Wow, that's insane. So it's not just a single object. It's changing how we understand the evolution of Well, everything.
Exactly. That's the beauty of studying these extreme objects. They push the limits of our knowledge and open up all these new avenues for exploration.
And the really exciting part is Porphyrion's discovery hints that there's a whole bunch more of these giants out there, just lurking, too faint for us to see right now.
A whole universe of hidden giants waiting to be discovered. As our telescopes get more powerful, we're going to be uncovering even larger structures. It's like we're constantly pushing the boundaries of what we thought was even possible in the universe.
Which brings us back to OE's research, right?
Oh,
You mentioned it changes our understanding of giant radio galaxies.
oh, absolutely.
So tell me, how did they even find over 11,000 of these giant radio galaxies?
Well, they started with this thing called the LOFAR 2-meter sky survey. LOTS SS for short.
Catchy.
Right. It's this ongoing project. Basically, they're mapping the northern sky in crazy detail using these low radio frequencies to pick up these really faint signals from super distant objects like these giant radio galaxies.
Okay, so even with a telescope as powerful as LOFAR, trying to find these giant radio galaxies must be like what? Finding a needle in a haystack, but like a cosmic haystack.
That's a great analogy. And you're right, it is a monumental task. That's where the machine learning comes in.
Oh, right. You said they use machine learning.
They did. They basically trained this algorithm to recognize the telltale signs of a giant radio galaxy, all within the LOTS data.
So the algorithm was like a super efficient cosmic detective.
Exactly. Scanning through millions of images, searching for the most promising candidates.
That's wild. But they didn't rely solely on this algorithm, did they?
You're right, they didn't. They wanted to be extra sure. So they combined the machine learning with, get this, citizen science.
Wait, really?
Yeah. They used a project called Radio Galaxy Zoo. Thousands of volunteers, just regular people, looked at these images,
Wow.
helping to classify these objects based on, well, how they looked in the radio images. It's amazing, really. Combining human intuition with cutting-edge technology led to this major breakthrough.
That's incredible. I love that people can contribute to these huge discoveries. So this new catalog, it must be a treasure trove of information. What are some of the key things astronomers are learning from it?
One of the most surprising, I think, is that giant radio galaxies, well, they might actually be way more common than we originally thought.
Really?
Yeah, their results suggest the number of these giants could be comparable to other luminous but smaller radio galaxies.
So the idea that giants are rare is being completely challenged.
It really is. And that has huge implications for how we think about how galaxies evolve and how these giant radio jets influence their surroundings.
Speaking of influence, let's talk about how these giants shape the cosmic web. You called them cosmic architects earlier.
Yeah, it's a good analogy. So think of the cosmic web like this giant network, right? Filaments, clusters of galaxies, all interspersed with these giant voids. Most of the universe is matter. It lives in these filaments.
Right, right.
And they're incredibly dynamic, always changing.
And these giant radio jets, they inject energy into these filaments, right? Sort of like shaking things up a bit.
That's it, exactly. Imagine these jets just blasting through the intergalactic medium, heating it up, creating shock waves, pushing matter around.
Like giant cosmic bulldozers, just
Wow.
reshaping the cosmic landscape.
Perfect. And this process, it really impacts where new galaxies form, how those galaxy clusters evolve. It's even possible these jets help magnetize the cosmic web, like seeding the magnetic fields we see today.
Wow, so they're not just amazing to look at, they're fundamental to how our universe, as we know it, even came to be.
That's the thing, they are. Now, remember how we talked about cosmic voids?
The vast empty spaces.
Well, OE's team, they suggested that these giant radio galaxies might be super important to how those voids are shaped. They calculated that Porphyrion,
Yeah.
it released as much energy as galaxy cluster mergers. And those are some of the most energetic events in the universe.
So these jets, they're powerful enough to influence the evolution of entire cosmic voids. That's incredible.
It is. And it gets even more interesting. They proposed that a bunch of these giants, they were around when the universe was a lot smaller.
Oh, wow.
So back in the early universe, these jets would have had a proportionally larger impact on their surroundings.
Because everything was closer together.
Exactly. Like if you have this massive construction project happening, it's going to have a much bigger impact in a small town than it would in a huge city, right?
Right, because the scale is so different.
Exactly. And this early activity, it could have had some really long-lasting consequences. For the evolution of the cosmic web, we're just starting to understand how influential these giants really are.
This is amazing.
Yeah.
So where do we go from here? Like, how do we unlock even more secrets about these cosmic giants?
Well, one thing is for sure, we need to find more of them. That
Right.
means even more powerful telescopes, pushing the limits of what we can detect.
You're talking about the square kilometer array, right?
Yeah.
I've heard it's going to be incredible.
It is. It's going to be a game changer. With the SKA, we'll be able to detect the fainter, more distant, giant radio galaxies. We'll be discovering a whole new population of these objects.
That's so exciting.
Yeah.
What else are astronomers looking at besides, building bigger telescopes?
Well, we really need to understand the nitty-gritty of these giant radio jets. Like, how do they form in the first place? And how do they travel such incredible distances without being broken apart?
Through all that stuff in space.
Right. And what role does the black hole play? We know it's there, at the heart of it all.
We've got a lot of questions, even after discovering Porphyrion.
We do. But that's what makes this field so exciting. We're constantly pushing the boundaries of our knowledge, uncovering new mysteries about the universe.
Okay, so speaking of mysteries, we touched on something called surface brightness selection earlier. You said it's one of the reasons we've missed so many of these giant radio galaxies.
Exactly.
So can you explain that a bit more?
Basically, all telescopes have a limit to what they can see. They can only detect objects that are bright enough.
Makes sense.
And we measure this brightness in terms of, well, surface brightness, how much light an object emits per unit area on the sky.
Okay, so a giant radio galaxy, even though it's huge, could actually have a lower surface brightness than a smaller one.
Exactly. Because the light is spread out over a much larger area, right?
Right, of course.
And that means a lot of giant radio galaxies, they're just too faint for our telescopes to see, especially the ones that are farther away or maybe just less powerful.
They get lost in the vastness of space.
You got it. It's like, imagine trying to spot a firefly in a field full of spotlights.
Ah, I see.
Those fireflies, they're there, but they're easily missed. And this has been a real problem. We've been biased towards seeing the smaller, brighter radio galaxies for, ever. And the giants have just been hiding in plain sight.
So how do we fix that? Besides the SKA, are there other ways to find these hidden giants?
Well, we can develop better data analysis techniques, ways to account for this surface brightness selection bias.
So we need smarter software to go with our more powerful hardware.
Exactly. And that's actually what OE's team has done. They created something called a statistical forward model.
Okay, try saying that 3 times fast.
Right. It's a mouthful. But basically, it takes this surface brightness selection into account and allows them to estimate the real population of giant radio galaxies, even the ones we can't see yet.
That's really impressive. So they're not just finding these giants, they're creating the tools to understand them and their place in the universe.
Exactly. And their model, well, it's revealing some really interesting things, like the surface brightness of these giant radio galaxies. It can be really different, even among giants that are roughly the same size.
So even among giants, there's diversity.
Absolutely. And that diversity tells us a lot about the physics of these jets, how they interact with their environment. It's like each giant radio galaxy has its own story, written in radio waves.
That's an amazing way to put it.
Yeah.
And it makes you wonder, what other stories are out there, just waiting to be heard?
Right. What other incredible giants are out there, hidden from our view?
It's mind-blowing, really.
Uh,
Well, thank you so much for, taking us along on this deep dive. It's been amazing.
the pleasure was all mine. I could talk about giant radio galaxies all day.
I bet you could.
Yeah.
And listeners, that's it for this deep dive. But remember, there's a whole universe out there just waiting to be discovered. Keep looking up.